Well, I've been obsessed with living forever my entire life. I've always wanted to make certain I was around when we discovered life on other planets and things like that. It's not a fear of dying has me obsessed with curing aging and stuff. My father was like that too. My father was one when I was 10 years old who actually suggested that I grow up, become a doctor, and find a cure for aging.
Even today, when you go around and tell people that aging is just a disease and it's something that's curable, it's like, oh, really? How come?
I went to an anti-aging conference one time, and I heard a guy named Bob Harley talk about telomeres. And I was kind of blown away because he started talking about how telomeres get shorter as cells divide. And he also suggested this might be why we age. This shortening of the telomeres might be the cause of aging. 3 months later, I discovered human telomeres. I was one of the inventors of human growth hormone, tissue plasminogen activator, erythropoietin, beta-seron, osteoinductive factor. I had a very, very successful career and actually became quite well known.
Hi, this is Liz Parrish, and this is my co-host, Saravanan. You have just come to the Buying Time podcast, and today, on episode 3, we're going to talk about telomeres.
Hi, Liz. I'm very excited to be in this podcast today. For the first time, we're going to have a guest, and what a guest he is. Why don't you introduce Bill to the rest of the audience? Both of you known each other for a long time.
Absolutely. So this is Dr. Bill Andrews. He is the founder and CEO of Sierra Sciences. He's also the originator of a whole bunch of science that you may or may not use in your life. And he has focused his career on an enzyme called telomerase reverse transcriptase. And I'm going to let Bill explain what he does to the audience. And when you are done with this podcast, you're going to know why telomeres are so important. Bill, take it away. What are telomeres?
You called me a person who's focused my life on telomeres, and it's actually more correctly to say I'm focused my life on trying to find a cure for aging. I've been obsessed with living forever my entire life. I've always wanted to make certain I was around when we discovered life on other planets and things like that. So it's not a fear of dying that has me obsessed with curing aging. It's a fear of missing out. And my father was like that too. My father was one when I was 10 years old who actually suggested that I grow up, become a doctor, and find a cure for aging. I don't know why nobody's done that yet. As if he thought the only reason we haven't cured aging is because nobody was interested in it.
It's something that even today people haven't figured out, that aging is a disease and that's curable. And Liz was talking about it at length in one of our earlier podcasts. Even today, when you go around and tell people that aging is just a disease and it's something that's curable, it's like, oh, really? How come? And you need to explain it for a long time. I saw in one of your videos where you talked about progeria as a disease and everybody's having maybe extended progeria and things. Amazing that somebody thought about it. It must have been like 50 years ago?
Early 1960s, when my father came to me and said that. Why was my pet dog dying of aging long before I was, when we're in the same environment? Made me start thinking that there had to be some kind of like switch in our cells or in our bodies that said, okay, it's time to start getting old or start getting unhealthy or stop fighting the diseases. Something had to be happening. None of the theories on aging made sense. They all were like based on environmental impacts to the body and essentially random events occurring and accumulating. Why was this causing us to age at different rates? Why did cancer and other diseases occur in our pets just at about the same time in their lifespan that occurs in humans? Okay, so like humans get cancer at a high rate when they're in their 40s, 50s, 60s. The dogs were getting them at the high rate when they were in their like 5-year-old, 6-year-old, 7-year-old, and it's like there was some switch that was turning off that was saying, okay, it's time for the body to quit being able to fight diseases as well. And so I kind of focused on the idea that accumulation of just damage didn't explain that. I also realized that our cells have the ability to replace themselves, because if we had a damaged cell, some other cell divides and just replaces that damaged cell. Why would our body, which is really a culture of cells, be any different than a culture of cells in a petri dish, bacteria or yeast or even human cells? But they can grow, and if any cell gets damaged, the other cells just outgrow those cells. They don't all become sick. They just outgrow those cells, and suddenly the culture is back to a healthy culture. Healthy cells can replace dead cells or damaged cells. So why does that cause us to age? Then why was there this kind of timing that there's a switch that gets shut off? Most of the theories did not explain the statistics of aging. If it was accumulation of random events, we would be expecting the aging curve of humans and other animals to be more like a normal curve. But it wasn't. It was like there's this long stretch where there's hardly any aging, then it just peaks and flops. Okay, so we all seem to have a die of old age at about the same time, relative at least to like a regular normal curve that's all random. I was so obsessed with this aging that I was, starting anti-aging clubs in high school, in college. And when I was in college, one of my best friends was a guy named Bruce Boiler, who actually ended up getting a Nobel Prize in medicine in, I think, 2010 or 2011 or something. But he and I, we would just spend all our time just wondering about the aging process and like, God, we got to be able to cure this. And he and I both volunteered in a fruit fly lab lab run by Dr. Dan Lindsley. And we just started doing experiments with fruit flies, trying to see if we could figure out anything about how to make them live longer and stuff. We spent our free time just talking and theorizing about the whole aging process and what it is all about. But then, like in the early 1970s, I ended up learning about the Hayflick levels, which was really very big impact on everything, because this whole idea of why don't our cells, our healthy cells, replace the damaged cells? Well, now all of a sudden there's this Hayflick limit, which is that human cells cannot divide indefinitely. When you take cells from a 10-year-old, put them in a petri dish, they can divide about 60 times before they stop dividing. When you take cells from a 50-year-old, they can divide maybe 30 times before they stop dividing. And then you take cells from a 90-year-old, and they can only divide like 5 times before they stop dividing. So there was something inside of our cells that was telling us that there's a limit to the number of cell divisions that occurs, and our cells know how many times they have divided already, and they know how many times they have left to divide. So me and Bruce Boiler, we used to talk all the time, how could inside of a cell, or how could cells evolve a system of timekeeping? I remember proposing one time that maybe there's something like ride tickets at an amusement park. You go to an amusement park, your mother gives you a bunch of tickets, and you take a ride and you rip off a ticket, they take a ticket. So you have less tickets. So now, let's say you start with 5 tickets, now you have 4 tickets. So you can say, well, I've been on one ride, I've got 4 rides left. You go on another ride, you have 3 tickets. You can say, well, I've been on 2 rides, you've got 3 rides left. Well, that kind of mechanism was kind of like a lot easier. It was the only way we could think of where a cell could keep track of how many cell divisions. That became my big focus. I wanted to go study find the ride tickets that would explain the Hayflick limit. Unfortunately, everybody at the time thought that Leonard Hayflick was wrong. They thought he just must have messed up. And people would say, yeah, nobody's ever been able to reproduce that data. I knew from my hands-on work with growing cultures of human and mouse cells, that it's really hard to grow cells so long to be able to actually measure to detect the Hayflick limit. So I knew that the reason why nobody's reproduced it was because it was an extremely difficult experiment to do. And Leonard Hayflick was just an artist. He was really, really good. Because the biggest problem was when you culture cells, you're always culturing, letting them grow a little, taking some out, opening the petri dish, taking some out, putting them in a new petri dish, let those grow, and take some of those out, put them in another petri dish, and let those grow. And risk of contamination from taking cells from one plate to another was so high that nobody could actually get those experiments completed. All through graduate school, I could find nobody that would let me do research in this area. And so finally, when I was getting my PhD in population genetics and population and molecular genetics, I decided I'd go postdoc in labs trying to find somebody that was interested in the Hayflick limit. And even then, I got accepted to every lab I applied to. But when I went to interview the labs to see if I wanted to work there, they all thought the Hayflick limit was meaningless, didn't make any sense at all, and they didn't believe it. They thought that couldn't possibly have anything to do with aging because it didn't make any sense. They didn't understand evolution enough to understand why such a thing would happen. And so when I got my PhD, I went into biotech instead and focused on cancer research, heart disease research, and inflammation research. That's where I had my big breakthrough. I ended up being very successful in my research. I ended up being second place for National Inventor of the Year for my cancer research. I was one of the inventors of human growth hormone, tissue plasminogen activator, erythropoietin, beta-seron, osteoinductive factor. I had a very, very successful career and actually became quite well known. But then here's where the telomeres come in. So I went to an anti-aging conference one time because I really wanted to get anti-aging going at the company I was working for at the time, which was called Parrish Biosciences. And I heard a guy named Calvin Harley talk about telomeres. And I was kind of blown away because he started talking about how telomeres get shorter as cells divide. He suggested that this might be the explanation for the Hayflick limit, which he believed in. And he also suggested this might be why we age. This shortening of the telomeres might be the cause of aging. So before he could even get off the podium, off the stage, I was at the bottom of the stairs, stairs to this podium. And I stopped him and I said, has anybody figured out how to lengthen telomeres? Because that would be the proof that these had things to do with aging. If somebody could lengthen telomeres and show age reversal. And he said, no, people have been working on it for years. And nobody's been able to figure it out, but they do know that 10 years earlier, there was an enzyme discovered in the labs of Elizabeth Blackburn and Carol Greider that actually was shown to lengthen telomeres in a pond scum organism called tetrahymena. And so Calvin Harley was saying that maybe humans have an enzyme that's similar to that. But it would only be produced in our reproductive cells, our germline cells, because our telomeres were shortening in the other cells, but in our reproductive cells, they couldn't be shortening. Otherwise, our children would be born with shorter telomeres than we have, and their children would be born with shorter telomeres than they have, and we would have been extinct as a species long, long time ago. So I said, Calvin, let me come and work with you, and I'll figure this out. And he knew of my successes with all these other things that I'd done in biotech. And so I essentially was hired on the spot. And 3 months later, I discovered human telomeres.
Can you explain what a telomere is? Where in your body are telomeres and what do they look like?
I don't like the analogy, but think of a shoelace. Okay, so on the tips of your shoelaces, there's these caps called agnets. Now, so those would be the telomeres of our chromosomes. Our chromosomes are made up of a long DNA molecule that's kind of like a shoelace. And at the very tips of our DNA molecules are these things like aglets called telomeres. It's just they get shorter and shorter and shorter. And the reason I don't like the analogy is because people like to think of telomere getting shorter as wearing and tearing, like our shoelaces do. Our shoelace aglets get shorter and shorter because of wear and tear. But that's not true for our telomeres, because our telomeres get shorter. They don't really get shorter. Every time a cell divides, everything inside that cell needs to be duplicated. The DNA has to be duplicated, and the new DNA is made shorter. Most people call it degrading or unraveling or all kinds of words, but the main reason our telomeres shorten is because our cells lack the ability to replicate, to duplicate the DNA all the way to the very ends.
Looks like telomere is just extension of normal DNA, and unlike egglets or shoe caps, this is nothing special. It's just the same DNA. Why do we call them telomeres, and why don't we just call them DNA?
Because when they were originally discovered, they were shown to stain differently, things like that, and it's because of the DNA sequence. So the DNA is made up of 4 bases, A, G, C, and T, and these bases are what code for the sequence of these bases is what codes for our eye color, hair color, things like that. But at the very tips of our chromosomes, all of a sudden there's a repeat sequence that starts as T, T, A, G, 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 T, T, O, G, 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 T, T, O, G, 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 repeated over and over again. And that is essentially just protecting our chromosomes. Now, the T, T, A, G, G, G sequences also play a role in gene regulation. Okay, they can actually, this will be more complicated, I think the audience wants to hear, but they can behave like enhancer sequences that can turn genes on and off at the promoter level. And
Wow.
so, but the shorter the telomere gets, the more difficult it is for the telomere to reach the genes that are on the chromosomes. So that affects our gene expression too. And that explains partially why we show signs of aging, okay, all through our lives, okay, because of the telomere shortening is actually affecting gene expression on our genes. So now the question that we had at the time, or there has to be something like telomeres in our reproductive cells to keep the telomere shortening in those reproductive cells. Because if telomere shortening was occurring every time our reproductive cells divided, I said our children would be born with shorter telomeres than we have, and their children born with shorter telomeres than they have. And we wouldn't have any DNA left after many generations. We would have been extinct a long time ago. So the start of this whole project was, okay, what's in a reproductive cell that's not in a normal cell? We found a lot of candidates, and then I took those candidates and did computer modeling, identified one of them, something we called TRC3 at the time, and I declared this as telomeres. And so since we said, okay, here's our number one candidate, we then went ahead and mutated the telomerase so that it would now produce a different sequence than TTAGGG. And so we put that back into cells, let cells grow for a while, and then we sequenced the telomeres and found out that the telomeres now were that sequence that we taught the new telomerase to make, which proved, that was the deciding proof, the major publication we had in 1993, I think it was, 1993, 1994, where we had published the sequence, the cloning and discovery of human telomeres. And so, now I don't want to make it sound like telomere shortening is the only cause of aging, but it's definitely an explanation for aging. And what it clearly is, because of the fact that our cells can only divide a certain number of times, no matter what else we do to try to prevent aging, nothing's ever going to work unless we also stop that telomere shortening. So the whole idea was we need to start having all of our cells, not just our reproductive cells, start producing telomeres to keep the telomeres, to keep them from shortening or actually lengthening them to possibly reverse aging. So we did all those experiments, published that in about 1998, where we showed that and place human cells in a petri dish. So when you take human cells and grow them in a petri dish, normal human cells, you can actually see gene expression patterns change with the number of cell divisions or with aging. But when we put telomerase in the cells, that didn't happen. The cells showed no signs of aging by every method of measurement that we knew of, and they never reached the infant.
Did it stop the aging at the point of the age of the cell when you added it, or did it actually reverse the DNA pattern to how youthful of a state?
Well, that was the exciting part, because we were hoping that it would stop, the cells would stop aging, but they did reverse by every method. So we looked at, because when we put excessive telomerase into the cells, we actually, and then measured telomeres, we saw the telomeres get enormously longer. And that had a tremendous effect on reversing all the gene expression patterns to young cells. So the old cells that got treated with telomerase became indistinguishable by every method of measurement we knew of, indistinguishable from regular young cells.
What is the change between a younger cell and older cell? I know that epigenetic changes are some of them. Can there also be some mutation along aging? If a person, a baby just born, and then the baby lives to about 70, 80, whatever, what are the changes that will be there in the gene? An individual's genes go through over a period of 70, 80 years time that extending telomeres is able to reverse.
First of all, there are going to be mutations that occur in cells. That's always going to happen. But every cell is going to have a different mutation. There's not going to be a mutation. And every person is going to have different mutations. So there's not going to be a mutation that causes aging. A lot of people say, well, it's the number of mutations you get. When you get to a certain, the more mutations you get, the older your cells get. But we have to go back to that concept before. We know from every other study ever done on cell growth, whether it's in a petri dish or an animal, that damaged cells can be replaced by healthy cells. Why isn't this happening? So I mean, the exception would be cancer, okay? Because cancer essentially is a healthier cell than we have. They just divide and divide and divide, and that's why they lose growth control. So cancer is the only exception. But even when you get cancer, our immune systems are very efficient at fighting cancers. And the only reason why our cancers become dominant when we get older is because the telomere shortening has affected our immune system, has made our immune system less likely to fight the cancer. It's called immune senescence. The cause of senescence in words is telomere shortening. I was taught in school that senescence was irreversible. Once a cell went into senescence, there was no way to take it back out of senescence. By producing telomeres and near senescent cells and senescent cells and even nerve cells, we just proved that whole theory. Okay, so no longer did people start saying that senescence was irreversible. We could now totally abolish senescence, and we could prevent cells from going into senescence. And a lab run by Woody Wright and Jerry Shea actually made an inducible telomerase gene where they could turn telomerase on and off, allowed the cells to get to senescent state, turn the gene on, and those cells came back out of senescence. So whole dogma of senescence just suddenly got changed. When we discovered telomerase, we also did an experiment to show that the antisense of telomerase would kill cancer cells by essentially causing the cancer cells to die of old age. So I was the key inventor of a drug called imeltastat that I designed to be an antisense oligo, essentially, not antisense DNA or RNA, that would inhibit telomerase in cancer cells. And in every cancer cell line that we tested that on, it killed those cancer cells. And so it was like one of the biggest breakthroughs in cancer research ever. I'd already was National Inventor of the Year for my cancer research. So I'd already done through a lot of clinical studies, developed a lot of cancer drugs, but my interest was aging. And now here I'm back to doing cancer research. I didn't want to stop anybody else from doing it, but I wanted to focus on aging. Geron Corporation had this board of directors meeting, and I gave a presentation where in like the same week I had demonstrated that we could cure aging in human cells and also cure cancer in human cells. And the investors, the head of the board of directors, bought up and said, okay, these are very exciting, but we can't do both. We have to focus on one. And so there was a discussion which would have the quickest return on investment, and they decided to focus on cancer. Curing cancer would get a quicker return on investment than curing aging. I argued, I said, if you inhibit telomerase, you will allow telomeres to get really short in those cancer cells, which will cause mutation rates to skyrocket, which means every cancer cell will find a way to come back. Okay, so inhibiting telomerase was a bad idea, I thought, and because it would make cancer decrease the cancer burden, but there would be so many mutations occurring that every cancer was going to come back, and that's actually what they're seeing nowadays. 30 years later, they're still doing clinical studies on imeltastat, and one of the big problems they're seeing is cancers always come back. I was very interested in aging, so I resigned at that time, along with Mike West, who was the founder, and a few other people that were more interested in aging than cancer. I started Sierra Sciences to focus on using the new telomerase discoveries to find a cure for aging. So I founded this company in 1998, and we've been working ever since then with one and only mission to try to cure aging through lengthening telomeres using the enzyme telomerase. Now, that doesn't mean that I don't think other things are causing aging too, but I've already said, I think nothing will ever cure aging unless we also stop telomere shortening. So I'm making that the priority. But after we get that all figured out, I do want to focus on the other things like oxidative stress and I think other things that cause aging, DNA damage, which is oxidative stress and things. So, but that's where we are now. There are roadblocks that I've run into have been mostly, investors. So I had no trouble finding investors. I had such a great career up till then that when I decided to start Sierra Sciences, I found investors right away. But I learned something. Investors, we always say investors invest in the people and not the company. Okay. So they were investing in me. Okay. But the thing is that they looked at me as a way of making a lot of money. Okay. So I had a dream of curing aging. They wanted to invest in that dream by making products that could be marketed, like antioxidants, things like that would make them give them a lot of quick return on their investment. And so they invested in the dream, but not the dream coming true, is what I always say. And so for 10 years, first 10 years of the company, I argued, let's get back to focusing on trying to make telomerase inside of our cells. They said, we'll get back to that later. And then things all went to pot with the global financial crisis of 2008. My investors went broke, and I took advantage of that to buy them all out and became the 100% owner of Sierra Sciences again, so that I could now be in control of the science. And we had about $3 million still in the bank. I ended up spending about $35 million from the investors on the research, but most of it was their research, not the research I wanted. So I spent the last $3 million looking for a chemical that would lengthen telomeres, so it would induce telomeres and lengthen telomeres. And we ended up finding something that we call C0314818, because it was the 314,818th chemical we tested. And that caused the production of telomerase to the level of about 16% of what we needed to stop telomere shortening. So that was a big discovery. And I ended up, because I now didn't have any investors, I ended up licensing that to companies, along with some natural products we discovered, to let them start selling it as a product. And we get royalties, which funded our research. So that's how we ended up getting our research. Well, just about that same time, I got a call from somebody named Elizabeth Parrish. And so I went and met with her because she was interested in helping us with research and providing us with funding. This is like 10 years ago. And so I was speaking at a conference in Vancouver, and I was getting ready to fly back to Reno, but she was in Seattle. So I stopped and, stopped in Seattle, my flight, got a taxi to this place where I met with Liz and one other person. And we talked for a while, and then I got back on my flight and went back to Reno. But Liz ended up becoming one of the biggest supporters of everything we're doing that I've ever met. And if you know her story, she ended up deciding that to really get this system going, she was going to volunteer to be treated with one of our gene therapies. Okay, so long before we discovered these molecules, these small molecules like C0314818, we had developed gene therapies. I've been doing gene therapy since the 1970s. I was first designed a way of curing, I can't remember the name of the disease. Tay-Sachs disease, and using gene therapy. But we had developed a lot of telomerase gene therapies where we had a gene therapy is where you have like a virus. And inside that virus is a gene. The rest of the virus is gone. There's nothing toxic about these viruses. They just become like taxi cabs for delivering a DNA to a cell. And so we developed all these telomerase gene therapies for delivering telomerase to cells. But we were only using them for research purposes. It was Liz's idea that we should start treating humans with that. And I said, well, I'd be afraid of the risks and things like that. Liz can tell you that story, but she volunteered to be the first recipient of telomerase gene therapy ever, and it's really escalated the field.
Yeah, that was interesting, because I remember you saying, Bill, that you guys would use the gene therapy and electrophoresis gel to test your molecules against, because the gene therapy could lengthen the telomeres, and you were trying to get something that had a band as strong as the gene therapy, but something that you could just take when you needed it and not take it when you don't.
Exactly. Well, I showed you our studies of these small molecules and showing how much telomerase was being produced as a result of these chemicals. But on the sides, there were these controls, these positive controls, which were gene therapy was producing more telomerase, like 30 times more telomerase than it was needed to lengthen telomeres. In fact, the telomeres would get really long all the time.
I said, yeah, let's go. Let's go. We know that works. So let's do it. And then I think we worked together for another year and a half before you made my gene therapy, because at that time, I think you guys used some of the other vectors that you said you don't want to use those vectors. And we waited to have a really good version of AAV to use, which is a common delivery for gene therapy.
If somebody is listening to it now in 2023, what can they do and what they can do in the near future?
Well, the biggest bottleneck that ever occurred was completely unexpected, and that was the COVID pandemic. Okay, so I was generating a lot of funding from go-to-market partners that were selling products that get discovered, and everybody quit buying their products when the pandemic started, and so our funding plummeted, and so our research kind of slowed down a lot. So I started looking for new go-to-market partners. Okay, so one of the things that I did is I put together a plan called the Sierra Holdings plan. It's not Sierra Sciences. Sierra Sciences is just research. The Sierra Holdings plan was a plan of how we could start a whole bunch of new go-to-market partners, find go-to-market partners, or get people to start new companies to start selling discoveries that we have made. And there's a lot of things. I have a list here somewhere.
Sorry for interrupting. It's a little amusing that you have a big list of things that can be commercialized right today in age reversal market. Do I understand it correctly?
Yes,
You're sitting on a long list of technologies that can be
yes,
commercialized right today in the
yes,
anti-aging industry.
Yep.
Yes, that's very interesting.
yes.
Well, Bill has amazing things. He's got everything from products that can go to market right away because they're nutraceutical based telomerase inducers to things that need to go through drug compliance to testing. He has ways to test telomeres that are more accurate than the companies that are around now. So it's actually, I'm always amazed.
There's also diagnostics. There's also anti-cancer things. Um, the list of potential companies that could be created from all of our discoveries probably approaches 1,000. Okay, but some of the things that I thought would go really quick if there was people that wanted to take on some of these things is food toppers. Okay, food topper is we discovered a lot of natural products and we discovered a lot of pharmaceutical products. Pharmaceuticals work a lot better than natural products, but a lot of people don't like pharmaceuticals. But we do have natural products that actually induce telomerase too. When you just put them on cells in a petri dish, those cells start producing telomerase. Well, imagine if you took these pharmaceuticals or the natural products, nutraceuticals, put them into a salt shaker and just sprinkle them on your food, okay, or your pet's food, okay? So that's one of the things. Now, people start saying, yeah, the FDA would never allow it, but these are already on the market, okay? There's already companies that are marketing our strongest pharmaceutical and our natural products all over the world. It's just that nobody's made a food topper. People have made skin creams out of them, things like that. And then these companies that are now selling skincare products with our telomerase inducers, they've done clinical studies, or they've gotten approvals. And so anybody that wants to take on any additional things in different territories, that's things like that, that's available. Now, I had mentioned that I was one of the discoverers of human growth hormone. I'm going to go to Helen. So human growth hormone, when I was first got into biotech, Genentech had discovered human growth hormone, but they couldn't produce it in a way that wouldn't cause immune reactions. Okay, so when human growth hormone was originally developed to make dwarfs grow tall, okay, at least baby dwarfs grow tall. And whenever they treated anybody with the human growth hormone, kids had severe immune reactions to human growth hormone because it wasn't 100% identical to human. It was produced in bacteria, and the bacteria would put an extra amino acid on the front end. So Genentech essentially hired me as a consultant to overcome that problem because it was my area of expertise of making one of the things. So I ended up creating a technology that allowed them to produce human growth hormone in bacteria. That human growth hormone was 100% identical to human growth hormone. And when it was treated on humans, it caused no immune reactions. Now here's the tricky part. They kept it a trade secret. They never published it. They never patented the technology for producing it. And so I have it here. Okay, so if somebody wants to now get into the human growth hormone market, and patents, even every patent that's ever been written is expired long time ago. Anybody who wants to, I can give them the technology to produce human growth hormone. They can sell it at a fraction of the rate that other companies are selling.
So what's the kind of investment that they should be making?
Well, they wouldn't have to invest anything in Sierra Sciences. They just have to license it from us and at no charge.
And all the machinery and all that they're going to buy, what is going to cost?
It would cost us about $650,000 to reassemble the whole process. But then they would have to spend more money to scale that up. If some company decided to take this on, they would have to bring in the staff and the bioreactors, and I would provide them with the bacteria strain. So that's the tricky part. So I would have to recreate that bacteria strain, okay, from everything I have here. I have all the equipment to do that, and tools and the DNA molecules to do that. Create that, and then do a pilot study with a small bioreactor, and then demonstrate that it works. It gives authentic human growth hormone. And I said that would cost us about $650,000 total And then they could then take that and roll it up in like 1,000-liter bioreactors, and go through the whole harvesting process, which is kind of easy, and then get approval that it was biologically safe, which is a standard thing to do, and start marketing. So that would be, so since I only do research, all I would be is an advisor for that. And the reason why I would do this is because in all the go-to-market partnerships I have right now, and the ones that I've had like 10 different go-to-market partnerships right now, there's 4 that are still in business. I ask for a 10% royalty on sales, and I use that money to do all of my research. Instead of getting investors or writing grants, I get all my research funding from royalties from go-to-market partners. And so that's why I developed this, what called Sierra Holdings. There's a list about gene therapies. Gene therapies are something that, of course, Liz is doing. Like, I'd love it if Liz could find enough money to take all these on, because she's the first person I'd want to take on these things. Her company, BioViva, is the leader in the world right now in terms of telomerase and anti-aging gene therapy stuff. In my clinical protocols, I first test the people, do baseline tests for their abilities to generate a cytotoxic T cell response. And after they get treated, I test for cytotoxic T cell responses. And if it's positive, I know exactly what to do to block the cytotoxic T cell response. And so those are things that I want to do if we could ever find the funding so that we can do the higher doses. In our in vitro studies have shown that we have to use some pretty high doses if we're actually going to expect to reverse aging. Okay, so now I'm the first one that will say that I believe that Liz Parrish's aging was reversed. I've known her for 10 years. She looks younger than she did life was better. But it's not scientific enough proof for me to prove it. And so I'm very interested in seeing somebody take on this clinical studies and going with finding the lowest dose that would cause reversal of aging. But I'm afraid that we might have to go to pretty high doses.
So what difference higher dosage makes?
A gene therapy is like a virus that infects the cell.
The virus doesn't replicate once you administer the gene therapy, right? So
not a replicating virus. It's just really the skeleton of a virus, just has the components that allow it to insert the DNA into the cell, and there's no replication. So there's no production of new viruses in the body. But the cell becomes essentially identified as a foreign body. But the more of this virus that you use, the more cells that get infected. And if you mount a cytotoxic T cell response, the higher number of cells get killed by that immune response. So a low dose, you can have a cytotoxic T cell response and survive because you only killed the infected cells, which maybe was like 2% of all the cells, or 1% of all the cells. But if we want to actually make people younger, we got to get 100% of the cells infected, or at least close to that. And the question is how much virus does it take, especially with AAV, to get 100% infection of cells? And there's a term called multiplicity of infection, where we can tell in a petri dish how many viruses do we have to use to get 50% of the cells infected. And what we find with some viruses like lentivirus, it's essentially we have to use one virus for every cell when we get 50% of the cells infected. But with AAV, we have to use 3,000 times as much. So we have to use 3,000 times as much virus as cells to get 50% of the cells. This is one of the reasons that Liz now is working on a new system. Can I talk about that, Liz?
Yeah, absolutely.
Okay, so she's working on a new virus called CMV, cytomegalovirus, which has a significant number of benefits for AAV. And now that's my big hope, is that turns out to be something useful. But in the meantime, while they're still studying CMV, AAV's available, ready to go now, if anybody wants to take it on. Okay, I've got the clinical protocols, everything ready to go.
What could an average person do to help slow the shortening of their telomeres? On an average day, you're an average person going about your life. What can you do?
As I mentioned, telomeres shorten as a result of cell division. The new DNA gets shorter because cell lack the ability to replicate all of it. Yeah. So inflammation and oxidative stress. Well, first let's talk about inflammation. Inflammation is going to cause these cells to divide faster. So the more inflammation you have, the more cell division you have, and the faster the telomeres get shorter. So anti-inflammatories, very, very important. Keep inflammation down. Check for inflammatory markers like CRP and things like that. Keep those very low. So inflammation is always going to accelerate aging because the number one cause of aging is a weakened immune system. And so as soon as the immune system starts to get old, you get old, and you become more susceptible to dying of all kinds of diseases. So anti-inflammatories are very important. Now, I said that telomeres don't actually shorten by wear and tear, but you can. Smokers, people who smoke, they have a lot of wear and tear to their telomeres. They have what I call accelerated telomere shortening because it generates things like free radicals that actually cause the DNA to break in the telomeres that specifically target the GGG sequences in the repeat sequence I mentioned before of TTA GGG. Causes the telomeres to break and get shorter at a faster rate. So and same with obesity, psychological stress, all kinds of things. Anything that would generate inflammation or free radicals will cause accelerated telomere shortening. So I promote antioxidants, anti-inflammatories. And then in addition to that, I promote the telomerase inducers. And there's a lot of companies now that sell telomerase inducers that are natural products, nutraceuticals. They're a lot weaker than the pharmaceuticals. But you can buy the pharmaceuticals, but there are companies, people can Google them and find who are marketing telomerase inducers that are either pharmaceuticals or nutraceuticals. And
do they work?
No, well, there's been clinical studies done on the pharmaceuticals. Nobody's done clinical studies on the nutraceuticals. Okay, except for one company, and I don't want to mention their names. They've done some clinical studies, but I think they're intentionally misinterpreting their data results. I hope that doesn't get me in trouble for saying that, because they're overhyping it. They're making it sound like it worked a lot better than it actually does, when it's actually one of the weakest telomerase inducers on the market.
So you're saying there's pharmaceutical drugs that could lengthen telomeres?
Yes.
Are they commonly used drugs for different conditions?
I mean, the companies that are marketing them sure would like them, but people are slow into taking them because of pharmaceuticals. But they have clinical studies that have been done showing that they do affect telomere.
Have you taken any of them, Bill?
I take all of it. I've got a whole rack next to my desk here of nutraceuticals and pharmaceuticals that I take all the time.
Would you mind telling us what you take?
Well, I don't want to give product names, but I can tell you that the chemical, like the pharmaceutical, is that C0314818. I'll tell you that the brand name for it is Tamilane.
Oh, you made that.
Stands for telomerase activating molecule 818. They didn't like my name, C0314818, so they changed the name. But there's a few companies that sell that as skin creams and supplements and things like that. Then there's a lot more companies that are marketing our nutraceuticals that we've discovered here. And I take those too. And I do take the one that I was mentioning before that kind of has some overhyping of results, but only because of the potential synergy. I think that the question is, why is the telomerase gene shut off to begin with? Why is it so strongly shut off? And I believe that there's multiple mechanisms shutting off called repressors. And I believe that some of these nutraceuticals and pharmaceuticals are deactivating some of the repressors while others are deactivating other repressors. So I'm just hoping that taking a bunch of them will inactivate the majority of the repressors and give me the maximum amount of telomerase. But I've been taking these for over 10 years.
Bill, if I may ask you, how old are you now?
I'm 71.
Okay.
And I'm very, very still athletic. I'm very, I compete all the time in ultra marathons. I'm actually getting ready to try to break the world speed record for running 100 miles for my age group. And I actually think it's going to be really easy because the most 70-year-olds are so slow. So I'm scheduled to make an attempt in October.
What else do you do to keep yourself young at your age, Bill? One is that you have talked about this pharmaceutical, and then you talked about the nutraceutical that provides you this synergistic benefit. And I also understand that you probably do a lot of running.
There's such a thing as not enough running. There's such a thing as too much running. Okay, by too much running, I mean pushing yourself too hard. Okay, because if you push yourself too hard when you're running, you induce oxidative stress, which will accelerate telomere shortening, accelerate aging. So I always say, keep it fun. Like I said, I'm going for this 100-mile record because it'll be easy. I probably wouldn't do it if it was something that's going to be really tough for me. Okay, so
that has to go on a frame somewhere. I'm going to do a 100-mile run because that's easy, and I'm 71.
Well, I've already broken a record for the most 100-mile races run in a single year by an individual. And
Lovely.
I thought that was incredibly easy. It was fun. I just, like right after I'd finished the race, I'd go out dancing and stuff. It's like, and other runners would be on the ground line suffering and things like that. I don't know. I think something about my lifestyle has made me a better endurance athlete then.
How long ago was it? How old were you when you did that world record?
The world record for the most 100 miles races, that was 1998. So that was 25 years. So I was 42, 44 at the time. I was competing in endurance races when I was 10 years old and lapping second place twice, things like that. So I've always been very competitive. All through high school or college, I was on the track team and the cross country team.
Bill, what about your diet? What do you eat?
I'm totally vegan, and I believe in no oils. I'm a big fan of Dr. Caldwell Esselstyn, who promotes an anti-inflammatory diet of no oils. Everybody hears about how great olive oil is and stuff like that, but actually it is bad. It induces inflammation, and it also causes your collateral arteries in your heart and other things to close up. So it increases risk of heart attacks and things like that. When your coronary arteries get clogged, you have a heart attack and you die. But if your collateral arteries are open, you don't even notice it because your collateral arteries are just as good at circulating blood into your heart than as your coronary arteries. And most people die from heart attacks because they're eating oils and their oils are clogging up their arteries. They're closing their collateral arteries. And when you look at a heart and you look at all the blood vessels, the collateral arteries outnumber the coronary arteries like 1,000-fold. So, there's all kinds of circulation of blood in the heart if you keep those collateral arteries open. I never put oil on my salads or anything like that. I totally balsamic vinegar dressing, this is from all dressing. Now, I eat a healthy diet of just foods that are vegan, that are not cooked in oil. I try to avoid peanuts too, because a lot of peanuts nuts are oils. And the book written by Caldwell Esselstyn, Dr. Caldwell Esselstyn. I'm trying to remember the name of the book. The Prevention and Reversal of Heart Disease. That book is the best book I think ever written on how to decrease inflammation in your diet.
Bill, usually people discover Esselstyn diet when they have a cardiac issue and then they go looking for a solution. This is the only thing that is that offers some kind of promise on reversal of arterial plaques. How did you discover? You're a person who's been running, you've been fit all through your life. How did you end up with Esselstyn diet? It's usually a little esoteric, not usually very common.
When I was still at Berlex Biosciences, I was head of the molecular biology division of the inflammation department. So I learned a lot about inflammation, and I learned, especially when I got really actively into aging, inflammation is the number one cause of accelerated aging. So I did everything I could to learn how to have a diet that was reduced that it did not cause inflammation. Most inflammation is caused by the foods we use. I get tested by a company called LCAT and another company called MRT. The tests are called LCAT and MRT. The company name. Those tests will identify the foods that you eat that cause inflammation. Everybody's different, so everybody's going to find there's foods that they can't eat that their friends can eat. And I get tested every year. I've been very big proponent of reducing inflammation in my life.
This is a food allergen test, is it?
No, because it's a sensitivity test. There's a difference between allergic reaction and a sensitivity. The allergy test will miss a lot of things. And the other thing is I do take a lot of supplements, and a lot of supplements for all kinds of different things. And I have found a book that is the best book ever written on supplements. And I highly recommend it to everybody that wants to take supplements. And that's a book written by Dr. Sandra Kaufman. It's called the Kaufman Protocol. Now, I've been speaking on stage at continuing medical education conferences, everything like that, about supplements that are anti-inflammatory, antioxidants, things like that. And I used to go over all this stuff. Now, after reading this book, and I'm writing the best review that book ever had, I now just say, go read that book. That book is the best book ever written.
You reminded me that is someone we'll have to have on the show for sure, Sandra Kaufman.
But there's a lot of important things to take, especially vitamin D and omega-3 fatty acids.
What level do you keep your vitamin D at, Bill? Your vitamin D levels, what level do you try to keep it?
You want it at 60 milligrams per deciliter. Okay, 60 to 100 milligrams per deciliter. To do that requires taking 5 to 10,000 IU per day.
Every day.
Now, people are shocked when I know that off the top of my head. That's what I do, because vitamin D is a great anti-inflammatory and it has so many other benefits to it. Vitamin D is one of those. Omega-3 fatty acids. I actually, since I'm a vegan, I don't take fish oils. I take synthetic omega-3 fatty acids. And it's called Vasepa, VASCEPA. It's a little more expensive.
Is it omega-3 or is it omega-3 precursor?
Omega-3 fatty acids.
Okay, so what you're taking is synthetic DHA and EPA. Why? Because we have a lot of vegetarian clients and we can't give them omega-3. So if it's a synthetic source of omega-3, that would make a lot of difference for them.
Yeah, what I take is synthetic EPA. Well, EPA will get converted into DHA. So EPA and DHA are the two most important. ALA is a third one. ALA, the main source of ALA is plants. Now, one of the reasons that I'm vegan is because there's another fatty acid called arachidonic acid that is very inflammatory. So not all omega-3 fatty acids, omega-6 fatty acids, things like that are anti-inflammatory. Some are very inflammatory. So GLA, which is an omega-6 fatty acid, is very anti-inflammatory. Whereas most omega-6 fatty acids are there's a whole subject of omegas for fatty acid metabolism and stuff like that. But so ALA comes from plants. And the reason I'm vegan, I don't eat meats, fish, fowl, and I don't take dairy products, is because those are all rich in arachidonic acid. And there's Floyd Chilton has written a book called Inflammation Nation. And that's a really good book too that I highly recommend. He talks a lot about AA, arachidonic acid. He talks plenty about arachidonic acid.
Arachidonic acid,
yeah.
And how much of omega-3 do you take in a day?
I take 2 grams a day.
of EPA.
Let's see. If I took when I used to take EPA and DHA, I used to take 1.2 grams of EPA and 600 milligrams of DHA.
Okay. Bill, I have a couple of follow-on questions. One is, first question that I wanted to find out is, if inflammation is such a major factor for aging, how do we measure inflammation reliably? Just if we just track the CRP, is it good enough? That's one question. And the second question I had was, what is the relationship between inflammation and aging? It's just antioxidant. It's probably not oxidative stress alone, right? That's a different mechanism. Oxidative stress is a different mechanism, and inflammation is a different mechanism. What is the relationship between how inflammation affects aging?
Okay, the way inflammation affects aging is by causing cells to divide faster, immune cells, and the telomeres get shorter faster. So the cells reach immune senescence faster. But inflammation also causes health problems in that it's the main cause of cardiovascular disease, plaque buildup. When people break open, dissect plaques, they're made up of inflammatory cells. Okay, inflammation is a major cause of heart disease, strokes, anything that, a lot of things that clog up blood vessels. Another great book is written by Dr. Amy Doneen, Doneen, that's all about inflammation and its role in cardiovascular disease. She really does a really good job of explaining how inflammation actually plays a role in cardiovascular disease. And she gives advice on how to prevent it. Now, part of that question was also, how do you measure? And CRP is actually a pretty good measurement. There's at least 6 or 7 different biomarkers. If you just Google, I can't remember off the top of my head, but if you just Google them, you can find that there's several different 6 or 7 popular biomarkers for measuring inflammation. But there's also so many things you can do to reduce inflammation too. And sometimes you don't need to measure inflammation because there's so many great ways to reduce it. But yeah, so definitely, like, I get my CRP measured every 3 months. Okay. And one of the things that causes inflammation is flush. Okay. And so after I run up under my race or something like that, I like to get my CRP measured to make certain that I didn't induce inflammation. And so usually my CRP score is undetectable. I think it's less than 0.3. So it can't measure below 0.3. I forget what the units are. But so that's why I say keep it fun. Inflammation. If you're one of these runners that run a marathon and you cross the finish line and your hands and knees throwing up, guaranteed your CRP score would be off charts. Let me ask you, Sar, where are you in India?
I'm in a place called Chennai. It's in southern India.
The reason I ask is because there's one of my favorite doctors is in India, in New Delhi. His name is Dr. Rajat, R-A-J-A-T, Shakhan. I don't know how to pronounce his last name, or spell his last name, but he talks a lot about running and inflammation and how to reduce inflammation. He and I have spoke at many conferences together. And I've actually gone to India to run some of his races. One of those was a race that was 222 kilometers. That's 138 miles through the Himalayas of northern India and Ladakh. I don't know if you're familiar with Ladakh and the city of Leh. I've run races up there at 18,000 feet elevation. And if I remember what those are in meters, I think that's about 5,500 meters elevation, which is like very hard to breathe. And so Dr. Rajat Shakhan is the guy who advises me on all that. He's also the race director for that race. He's a really good doctor, and you should connect.
I would love to connect with him.
We'll have to interview this gentleman on running, because that is definitely a way for some people to stay healthy and live longer.
And some people who has never run in their life, like yours truly, should learn how to start doing it at such an old age without injuring something.
Well, endurance exercise. Endurance, it doesn't matter if you run or ride a bike or kayak or what. doing endurance exercise is probably the best thing you can do for yourself, as long as you don't push it too hard. Okay, it's called a Goldilocks effect. So it's like, this bed is too hard, this bed is too soft, this bed is just perfect. Well, with the Goldilocks so there's such a thing as running too much, running too little. There's just the right area, and the way to know you're in that right area is to keep it fun. Just say to yourself, God, this is so much fun. I hope it never ends. That's the way to do it. And it's like, I run every single day, but I run very casual. I like to sprint up hills every once in a while, things like that. But I keep it fun. I never push myself.
I think that we have talked about a lot, and we're actually over time, which is fantastic. And it was great to have you here, Bill, with us and with everyone who's watching and learning how to buy time in their life. I think keep it fun is definitely something to hang on, to end on. And if we decide to talk about more, we're just going to have to do a different podcast. So we'll have you back. How about that?
I would love to talk about cancer.
Oh,
so
my gosh.
Thank you very much for having me.
Would love to have you talk about that as well.
That's a very interesting topic. Thanks for coming over today, Bill. So this is beautiful. In fact, I'm so thrilled that we got the original inventor of telomerase and original inventor of synthetic growth hormone. I'm familiar with the story that you're talking about, growth hormone that was analogous and not bioidentical, giving a lot of problem. It gave a lot of bad name to hormone therapy today, using non-bioidentical growth hormone and damaging a lot of health, and non-bioidentical progesterone, primarily in which causing a lot of cancer. These are the two things that the entire hormone industry is suffering from even today. Hormone treatment is considered to be bad name even today. I'm happy to know that we spoke to one person who is instrumental in that disaster from continuing, stopping that disaster from continuing. So proud. Thanks for being with us today, Bill.
Thank you.
Liz, thanks for inviting Bill as our first guest.
Absolutely. And again, Bill, we'll have you back, I'm sure, probably more than once. Thank you for being here. And I hope that everyone who was listening enjoyed the conversation. I hope you learned something. And most of all, keep having fun.